Okay, let's end with the 5 assumptions we have to make when we do linear regression, and how to test them and what to do about them. The first one is linearity. Just like correlations, the whole idea of linear regression assumes that the relationship between x and y is linear. If it's clearly not, then linear regression is not the appropriate method. It also assumes normality, that the residuals are, and I put nearly, the residuals are normally distributed. If they're not, then you can get strange biases in your estimates of the model. But it's not, normality is not a terrible violation, or a terrible assumption to violate a little bit. This one is hard to say. Homoskedasticity. You have to have a lot of coffee, you can say it properly. Homoskedasticity. You might know it as homogeneity of variance. It's the same idea. The assumption is that there's constant variance in y across the range of x. And we'll see what that means. There's also an assumption that there aren't any extreme outliers in the data that disproportionately affect your estimate of the model. And then the last one is independence. Each observation in your data set should be independent of the others. Okay, how do we test linearity? The best test of linearity is to use your brain, use your eyes and your brain. Look at the data, plot the data. This looks linear. This looks like there might be a little bend in it. This looks just like a cloud. The more quantitative, the sort of extra step to do is to plot not x versus y, but to plot the residuals against x. Remember, the residuals are each data point minus the linear model estimate, y minus y hat. And if the data are linear, then the residuals should show no particular pattern across the range of x. They should be randomly distributed around 0. Some are above, some are below, and it's sort of random. If you see a pattern in the residuals like this curve, that means that the line that went through the data points did not fit them in a linear fashion. These ones are underestimates, then there's an overestimate, then there's an underestimate. Under, over, under. So these two indicate you're okay for linearity. This one indicates, nah, this is probably not a linear relationship. Does that make sense? Is there a quantitative way to test linearity? Is there a numerical way? Any ideas? Well, we sort of saw R squared already, right? R squared literally tells you something about how well the model fits. Although it doesn't really distinguish between a model that doesn't fit very well because there's a nonlinearity and a model that doesn't fit very well because it's just a giant cloud, right? Both would produce the same R squared. So best to use plots at this stage. Normality assumption, you can just plot a histogram of the residuals. And the histogram of the residuals is what is supposed to be normally distributed, a bell-shaped curve, a mean of 0 and sort of symmetric on both sides. So that's a visual way of checking. There's another visual way of checking called a QQ plot. Q stands for quantile. Yes, quantile, sorry. I don't want to get into exactly how these things are computed. The bottom line is, if the dots fall along a straight line in a QQ plot, then that is consistent with normality. If the dots do not fall along a straight line in a QQ plot, that's an indication that the data are not normally distributed. You can read up in the Navarro text about exactly the meaning of these two axes. But that's the bottom line about normality. There is a statistical test for normality called the Shapiro test, and in R, Shapiro dot test will do it. The null hypothesis of that test is that the data are normally distributed. The alternate hypothesis is that the data are not normally distributed. So you want this test to have a p-value that's high. Unlike most statistical tests, you want this one to fail. Because if the p-value is small for this test, it means the alternate hypothesis is probably true. And you do the test on the residuals. Shapiro dot test of residuals of your model. My dot mod would be the output of the LM command. Okay, so for normality, you can look at the data two ways, and you can do a Shapiro test on the residuals and hope that the Shapiro test fails to be significant, because that means the data are normal. Homoskedasticity, otherwise known as homogeneity of variance, is the assumption that the variance in the y variable, kind of the vertical variability, is constant across the range of x. So that would be consistent with homoskedasticity, and this would be heteroskedasticity. The variance in the y variable is different across the range of x. When x is small, the variance in y is small. When x is big, the variance in y is big. That's just one pattern. There's an infinite number of ways in which the variance in y could be different across the range of x. It could go up and down, it could go down and up, it could wiggle around. The assumption is the variance is the same. So the first way to look at it is to plot the data and just look at it with your eyes. Or you can plot the residuals. If the residuals are just equal across the range of x in terms of their variability, then you're okay. If you see an obvious pattern where the residuals get worse, bigger or smaller and bigger, bigger and smaller across x, then that would be a warning sign that you have heteroskedasticity. There's a test called the Brush-Pagan test. It has nothing to do with paganism. I think pagan is the name of someone who came up with the test. And it's a quantitative way of testing that assumption. It's also sometimes called the non-constant variance test. And there's two ways you can do it. BP test will do this test, and then if you load a package called car, there's a test called NCV test. The null hypothesis is that everything's okay, homoskedasticity. The alternate hypothesis is that you have a problem, that there's non-constant variance. So just like the Shapiro test, you want this test to fail. You want the p-value to be big. You don't want to reject the null hypothesis. The null hypothesis is that everything's okay. And you can use the NCV test and apply it to the model object from the linear model command. Okay, so we've got linearity, normality, and homoskedasticity. The next one is outliers. Obviously, you don't want to base your model fit on data that includes a crazy outlier. This line of best fit is fit just to those data points. If we refit that line and included this outlier, we'd get a line that probably comes down like this and tries to sort of minimize that big error at the expense of fitting these data points here. So we don't want a situation where a single data point disproportionately moves around our line of best fit. So the first thing, as usual, to do is plot the data and just look at it. We're really good at spotting patterns visually. Clearly that guy looks like an outlier. You can plot the residuals to see even more clearly data points that are much different than the rest. So that would be an example of an outlier. Here's an outlier of a different kind. It sits outside the neighborhood of the other data points, but it's sort of in the right direction, right? It's consistent with the line of best fit. Here's an example where our data point's above. So plot the data. There's a quantitative measure called Cook's distance, which you can read about in the Navarro text. And it's a quantitative measure of, like I said, how much each data point individually, whether it's present or absent, influences the estimate of the line of best fit. So it kind of does a thing where it takes your data set, and for each point in the data set, it removes the data point, fits the line, puts the data point back in and fits the line again, and compares those two model fits, those two lines. And if they're not much different, then that data point doesn't make a huge difference whether it's there or not. If it finds a data point where if you take it out, the line drastically changes, and if you put it back in, the line drastically changes back, that's a warning sign that, well, you've got a single data point here that changes everything, and that's probably an outlier. Okay, independence. The fifth one is independence of data points. There's no test to do for whether the data observations are independent from each other. That's something that you just have to think about conceptually when you collect the data. If you're collecting data from members of the same household, they're probably not independent from each other compared to if you're randomly selecting people in the population. So it's a question you really have to know conceptually in advance. What to do about the violations? For outliers, remove them. Kick them out of your data set. For homoscedasticity, you could consider transforming the dependent variable. That's when you apply a transformation like a square root or a cosine. There's a whole laundry list of ways to transform your data to fix problems with it. The problem with transforming your data is then, if you're doing stats on transformed data, all your conclusions are in the domain of this transformed version, and so it's a little hard to deal with. There's also this thing called weighted regression, where you downweight values in the range where variability is high, but we're not going to cover that stuff. Same thing for normality. You can consider transforming the data. We're not going to cover that stuff here. And for linearity, if your data aren't linear, then don't use a linear model, is the bottom line. If you want to model data that's not linear, then you have to use a nonlinear technique, which exist, but they don't exist this semester. Okay, that's it for today. Yes, one question.
In terms of the confidence intervals, I know you're saying like you don't like them because you don't like them. So what do we actually have to know about anything?
Do you actually have to know about confidence intervals? That's a good question. I have to check.
Yeah, like maybe it's like I don't know if there's going to be a class. Pardon?
Let me check.
Okay, because I just know like what to know about that.
Yeah, it is covered in the readings. So, and I just plugged it up.
Okay.
Well, okay, so
Let me check and see.
Okay.
It has to be in next week.